and they do a lot of really cool Python and Django stuff. He's going to be speaking on scaling Django and like multiple caching methods. Yeah, cool. Welcome very much.
Thanks for stealing my first two slides. Right. Yes, I do work for Breakouts. You would have seen our name as one of the sponsors. That's actually our sister company, it's Django. They're in the non-profit space. We are purely in it for the money. But we share the same engineering principles in the end. Right, so what we do at Breakout really is a very familiar stack to everyone over here. We've got Django, which from the previous talk, I saw that most people know what Django is. We do Twisted. Who knows Twisted? Yeah, well, liars. Twisted is really tough. Twisted, and then I have to give a shout out to a lot of our front-end developers who are here, who do React, and that's why I listed it there. Also, all the other popular things, I'm not going to list them all, but with Postgres and those things mean anything to you, we do that. Right. So the type of things that we do is, I'm just going to say that we mostly do websites, even though we do other more interesting things around it, like chatbots. We did some work for Facebook recently with a chatbot. But today's talk is mostly about websites and the challenges that we face. So everyone always says this, our systems handle large amounts of traffic, which I guess is true. And in the end, we want to be able to run these with a minimum amount of resources. So what's the problem that we usually face with this? Things break at scale. So let's take an example to illustrate how things can go wrong really quickly. Let's say you have a site, it takes 10 milliseconds to complete a request. So basically, your Django will hit the database on each request, does a bit of logic, nothing strange there, it renders a template, sends a response back, and this is all great. It takes 10 milliseconds, and you feel very chuffed about yourself. However, the situation changes very, very quickly if you do something and suddenly you get an influx of visitors to one of your systems. So if we use this example, let's say you have 1,000 concurrent people, and on average they do a request every 5 seconds. It means that every 5 seconds suddenly you need 10,000 times 10 milliseconds of, let's call it system time. So you end up at 10 seconds. So effectively you're under provisioned at that stage, and your site's going to go down, and that's pretty bad. And it's happened to every one of us. In fact, when we outsourced quite a lot, one of our suppliers delivered us a site which was supposed to be for a major radio station, and when we ran it, we do 4 concurrent requests per second, which was pathetic. And yeah, lessons learned over the years. Right, so what we want to do, also, it's actually much worse. That example that I gave, it ended up at 10 seconds, but it's not. Things do not get worse linearly. It gets worse much, much faster. A typical example is the database can only handle a certain number of connections. So sure, you can crank it up, but that's not really solving the problem. So without connection pooling, all your thousands of requests coming in, if they all have to hit the database, they're going to get queued, and some of them are just going to time out. So that's a typical thing. You may exceed the amount of bandwidth on the physical NIC, which has happened to us once when we were hosting on Exner, and there was an earthquake in Joburg. Everyone went insane, and the amount of traffic we peaked at about, we needed to sustain close to a gigabit per second, and we couldn't actually do it over the NIC. So these things happen as well. And then other dumb things that happen, maximum number of open files. There are literally a million things that can go wrong when you fail at scale. So we've got a few options to be able to solve this, and this whole talk is about that. So let's look at our first one. So we can add more hardware. And when I put up this slide, I didn't realize I was going to stand next to the Oracle banner. So don't worry too much about it. On the next slide, I completely mistake a lot for their taxonomy. Sorry, taxonomy. But okay, so look, sometimes you have to add more hardware to solve the problem, but that would make for an extremely boring Python talk if I were to end it right here. So let's explore a few other options. You can rewrite it in another language. Rewrite it in Go. this is the Titanic, and these are deck chairs, so make your own conclusions there. Now look, mostly you're not really solving the problem if you do that. There's an upper limit to what you can actually achieve. And sometimes you have to rewrite, or you can rewrite portions. It's a completely valid strategy, but once again, this is Python, not ScaleConf, so let's find something else. Right, so we want to fix the real problem. And I know there are a million ways of fixing the problem, but we want to focus on solving it through caching. So caching is this amazing thing, really. Caching can be hard when it comes to invalidation. It's also effectively a plaster. If you've got a gaping wound, you're not supposed to put a piece of bandage over it. But caching buys you a lot of time. It's kind of like morphine, I guess. In the end, you're probably going to die. But the point is, you'll be laying it for a long time. So let's use this hammer that we have at our disposal. So in every single system, this is just, there are more points, but these are the typical ones. You identify the points that you can apply the caching to. So from the bottom up, really, Django templates can do some fragment caching within the template, or in your Python code within the views, and cache there. You can try and cache the database queries, and drop in a reverse caching proxy at the web server level, something like Varnish or Nginx. And then the browser itself is also a cache, because the browser always checks locally first if it has something available. Let's talk about these ones. So Django template fragment caching is actually quite simple. It's got this nice little template tag available called cache. You just give it a time, identifier, and then you just give it enough parameters to be able to uniquely identify what's going to be happening on the inside. So this is fairly minimal. You've got an object and the modified time, so if the object changes, the next time it's not going to hit the cache because the cache key would have changed, and it has to fetch fresh data and then populate the cache again. You can do it in your view code. This is very similar to what we had in the previous talk, really. It's a very common caching pattern. Check the cache. If it's there, return it. Otherwise, do the work, store it, return it. I'm not going to belabor that point. You can cache database queries if you want to, but I'm really not a fan of this, and purely because it gets hard to figure out where things went wrong. You are kind of left with an inconsistent state in many cases, and I just don't have the energy to try and do this, so that's my excuse. Then you can do a reverse caching proxy. So this is a very common technique all over the web. It's and I've put in a few lines here, which it's contextless, but it kind of tells you how to tweak Nginx to act as a reverse caching proxy. So this is it looks like cargo culting, and in many cases it is. But basically, you tell Nginx, listen, you are going to act as a reverse caching proxy. You set a few of these directives, and then it will merrily start to cache things for you. This is a hammer approach. This is not a very good thing to do just like that. You need other techniques, and we will get to that. By the way, I'm just going quicker since we are out of time really, and I know we want to go to lunch. So let's go. The browser itself. The browser will look at the visited URLs in its history, and it will honor any caching headers that have been set on it. Right, caching backends. There are quite a few of them, and they're all very in how powerful they are. So the in-memory one is extremely simple in Django. You can just switch it on, but the problem is it's not really a good idea. It's not really a caching backend, and then you can't share the cache between different Django processes because the memory use is intrinsically tied to the Django process currently running. So you can use a database, which would be really stupid, because what's going to happen is you are mostly I/O constrained in many web systems. So CPU is fairly cheap. You usually have a lot of CPU available to you, but when it comes to I/O, you should not be doing many writes to your database and use it as a caching backend. I quite like memcache. The previous talk also loved memcache, and the reason why is it's so ubiquitous. Everyone uses it. It's very simple to implement. You can share the caches. It doesn't cluster, but you can pool it, and it's a very simple thing to debug with Telnet interface. And yes, there are many more caching backends. I mean, you can use Redis, millions of these, but we don't care about those right now. We only care about memcache for this talk. Okay, So let's talk a bit about the template fragment caching, because this is the easiest spot to get really quick gains. So we use a Django product called Django Ultra Cache, and it does a fair amount of work for us. It's like the hash template tag that you get standard with Django, but it does a few more things. So it cares about the sites framework. Django has this thing where each process is tied to a certain site. So if you have multiple sites that form a logical whole, then you use the sites framework. It also allows undefined variables to be passed as arguments. So you would have seen in the previous slide, or one of the previous ones, I did object.id, object.modified. Sometimes you've got arguments in there that are not necessarily going to be defined. The normal caching tag will break, but this one just merely keeps going. So it makes for a nice and clean template without if blocks to be able to handle the presence of the variables. And then the biggest thing really is it is aware of model objects that are subjected to its caching. So when an object is modified, then all the affected cache keys are found and they are automatically expired. So it means that what you can do is you can set longer expiry times in your cache tags, and you don't have to worry about stale content because we use the signals, use Django signals to listen to when things are happening, and it will find the caches and expire them immediately. So you always have a nice fresh set of data in Memcache. Right. This is the one that I actually record. Basically, undefined properties there. I've just got a few examples of it. This will still work perfectly. Then also, how it works is very similar to how the Django cache template tag works. You can nest them within each other. So what we're doing here is we've got an outer one that is cached, and inside there are two different ones. This one works on object 1, and that one on object 2. And what happens is, so effectively you're going to have 3 cache keys behind the scenes. So what happens is, if you were to edit object 1 and the post-save signal handler fires, that cache is expired, but this one is preserved. Which means the next time that you render it, you don't have to do any hard work in that bit. So also, we should talk about how you pick a good cache key. I had object.id and object.modified in there as my cache key, which is a fairly common pattern. But what you really need is a good key contains the minimum amount of information that determines the content inside the cache tag. Which means whatever you put in there, if any of those things change, you should assume that what's inside is going to change. You want to keep it as small as possible so that you don't do unnecessary work. We're going to look at a few examples. So if we look at the first one, what we've got here, you'll see that we also have to render a category inside, which means what you want to do is you've got the object ID, but you also want to consider the category that is going to be inside, because if someone edits the category in the backend, then this should change, and that is why you mix that into your cache key as well. So that's a very good one. Something like this is probably going to be bad, because what's going to happen is you didn't consider the category at all. So you're going to have to wait. I'm missing a time out there. You are going to have to wait a while for this entire thing to expire before it's going to reflect the new category title in your rendered content. So this is not a good cache key that was picked there. This is probably pointless, because if you have users that are logged in, then every user is going to have its own little cached version, which is really stupid, and you're going to end up exceeding your memory. And this really is insane. If you were to take request.get full path, this takes into account query string parameters. So if someone appends foo equals bar to the URL, then it's going to bust through your cache every single time. That's a terrible cache key. You can think if you put stuff in there like datetime or random numbers, even worse. Right, so just quickly on how it works. You have to be able to record what's going on with the objects inside the template. And the easiest way to do it is you have to do a monkey patch. So notice it's a monkey patch, and it needs to be done, otherwise it doesn't work. But basically, when a template renders, you jump into the template machinery, and at that point, you can start keeping track of the objects that are inside you, and then you know that eventually those objects influence what your template is going to look like, and that's how we keep track of it. So, yeah, basically it keeps a registry in the caching backend. We'll spend a bit of time on how that registry actually looks. And then, as I mentioned before, the post-save signal handler, it monitors the objects for changes and it expires the appropriate cache keys. Okay, so the registry, what it does is, think of it as tuples. It cares about the content type ID and then the object's primary key. Anything in Django that ends up being registered through the content type registry, you can uniquely identify with the combination of those two. So that basically means this content type and this object, it appears in these cache keys. And we do the same with the second one really, and then what we do there, we also know in which paths they will appear. We will meet this later on. So these two are very similar, and that is the registry that we keep behind the scenes. What we also do is we take a lot of care to rotate the size of that thing so that you don't exceed Memcache's maximum value size. Then the second one is we care about the content types themselves. So note no object in here. We know that, let's say this content type is an article. We know that cache key 1 and 2, they have articles inside them. And the same there, we know that these paths have this content type inside them. The reason why you do that is it's very easy when an object changes to go and find where it was, because the object already exists. So it will only ever use, it only really needs that. And that, however, if you were to add a new item, a completely new item, there is no object that exists yet. It doesn't, you don't know in which caches it is going to appear. So, but you know what the content type of the object is, which means that, so what you will do is, let's say I add an article, a completely new one, and it's supposed to appear on my front end. It will know that the content type appears in these things, and it will go and expire them as well. So it's a hammer approach to be able to get new items to actually appear on the site. So, modification and deletion, simple, because the object already exists. Cheaper lookup, best to expire. Addition, a bit more expensive behind the scenes. Right, so this is the template fragment caching. You can also, as you go up in how Django sticks things together, the template is at its lowest level, the view sits on top of it, and so on and so on. So what we can do is we can also cache the entire view if we want to, and it follows the same rules really. So if we were to look at it, we just apply a decorator to it. These are just examples of what you can add in there. And the idea is, what's very important is, the key is computed and it doesn't require any database lookups to be made, because that is another bottleneck if you make your key computation slow. So it uses that to figure out what a good key is. And implicitly, it will know what path, it will actually know what the get full URL was that you were called, that was used to get to this view, and it will add that into the caching key for you. But you can override that, and in other words, get full path. It adds the query string in there. So once again, people who add foo equals path to the query string can drill through your cache. So if you know for a fact that your view does not care about what's on the query string, which most Django views do, we build it into the actual regex for the old pattern. We try to not use the question mark foo equals bar bit. Then you just change that and you say use request dot path info, and it will be a smaller cache, a smaller, more targeted cache key. Right. Just to show that you can also use the decorator in rules.py. Right, and this basically, it kind of completes the Django part of it. The flip side to it is the reverse caching proxy, and how you glue all these things together to make a really robust and fast system. So for that, you're going to need a bit of theory. Luckily it's not too hard. We've got a few HTTP headers that have been with us for a long, long time. If I knew this talk was going to start after 12, that would have been 12. But it's an 11 for today. Last modified, when you receive something from a web server, it tells you this is the date, or this is the exact timestamp that this thing was generated. So that should be familiar to most people. We use a simple form of cache control. This tells it this item is allowed to be 20 minutes old. After that, it should be fetched again. But this one is very special. This is only ever interpreted by the browser. So these, all three can be interpreted by the browser. These two are only ever interpreted by the reverse caching proxy. And so what it means is and in the next examples we'll go through a timeline and I'll show you how it works. So let's say we've got a page which was generated at 11 o'clock, and this is the first time, cold cache. We start with the cold cache completely. The user navigates to a link and it hits it. So what will happen is the browser will make a connection to the server. I'm obviously skipping a few steps, but the browser will hit Nginx. Nginx will then go upstream to Django. It gets a response. Nginx will cache it within itself. The browser receives the response, and the browser itself will cache the response, depending on the caching headers that it receives. So this was at 1 minute past 11. At 30 seconds later, the user does the same thing. So he clicks the link, the browser checks the local cache. It immediately finds the cached version. And then it does this comparison. It compares last modified plus the Excel expires header. And if it is not greater, it renders it locally. So you'll see it doesn't care about max age. The browser first checks this thing if it is present, not max age. And then, now a minute later, user does the same thing again. The browser checks the local cache. It finds the cache version, but it sees that the time is greater than last modified plus the expires. So now the browser goes and asks Nginx because it thinks it's expired locally. Now Nginx does a different check. It checks the local cache, it finds it, but look at the comparison that Nginx does. It compares it to last modified plus max age, and then it returns a not modified. So you save quite a lot on bandwidth right there, and the browser receives it, and we keep going. And then a lot later, everything has probably expired by this stage. The browser will find the cached version is definitely expired. You need Nginx. Nginx does that comparison, last modified plus max age. It sees that it's completely expired. And now Nginx will ask Django again, please refresh my cache. Or it will ask Django for a new response, and it will refresh its own cache, and then we're kind of back where we started. Right. What's interesting with using the XXL expires header is if you have thousands of connected clients and we're working towards being able to expire everything for everyone, then what you want to do is you want your browsers, you want your clients to check frequently whether there's a new version available, because it means within 2 minutes perhaps your clients can get the fresh content in there. If they would, so you want to cache it for long within Nginx itself for 20 minutes, but you want your actual browsers to check quicker, more frequently than that. And that is why you use the two different headers. So typically you want your browser to check 10 times more than Nginx would actually go and talk to Django. And when you start doing that, then it opens up the world of purging and the reverse caches. Okay. Well, first off, the bit I skipped over, there's a little bit of Django there. It's a middleware. We kind of need, because Nginx needs to get these headers from somewhere. Django is not magically going to set these headers for you, and we have to give downstream, which is Nginx, we have to give it a few more headers. So this is a very simple example here, just a dictionary that is seconds, and we just have a few regexes there that we pre-compile. So anything that matches that will be cached for 30 seconds. Anything that matches that, 60 seconds. That's it. And then to make use of it, this is a vastly simplified example. your default policy must always be no cache. Otherwise, the moment you add caching headers to Nginx, it will try and cache everything. So you start off with please don't cache. And then you only care about get and head requests. All we're doing here is we're just figuring out what the actual age should be. And then the interesting thing there, we set the last modified header. There we set the expires header, and then max age. So we set them to different values effectively. And then importantly, we set a vary header as well. Vary headers are cool. It means that all over the world you get these transparent web caches that float around, and they are very stupid. So you cannot assume too much. So the thing is, Nginx can take, you can craft a special cache key for it. In other words, the default is to take the protocol, the server, the path, query strings, everything. That is your default cache key that nearly all transparent proxies will use, as they should. You should not make any assumptions and hack things into that, even though Nginx would allow you to do it. Because the moment you attach logic to your own special cache key, no one else in the world will know what you did. Vary headers. So vary headers are additive. You can add as many in there as you want, and then every single transparent proxy in the world will know. You take the default, which is the full path, and you add vary headers onto it, and that is how any proxy determines the cache key. It makes it work with Akamai and Cloudflare, all those things. That's how you really scale it up. Right. So all that's great. The last bit that remains is now we've got all these Nginxes with reverse caches, nice and warm, everything is fast, but when something changes in Django, we need to be able to tell all our nodes, we're done with this, please evict it from your own reverse cache. So that's a hard problem, because each node that we have, it runs Nginx as a web server, and the reverse cache is on that. The nodes are independent of each other. Typical web scenario, really. As it should be. One node shouldn't know that I am number one in a cluster of web nodes. We've got, I used to work with someone called Colin. He used to say, stone it, shoot the node in the head. When something goes wrong with a node, you execute it immediately. Just start up a new one, because they don't know about each other. They're not a family, they're not going to kill if one dies. So, well, sorry, a lot of death in my talk. Okay, so the nodes have no knowledge of each other, and Django doesn't know anything about the nodes, as it shouldn't. How can it know about these nodes? These are just things that are there. Django is only concerned with being an application framework and pushing out responses. So we need to find a way where we can broadcast a purge instruction to tell all these nodes, please clear these things from your reverse cache. And for that we use RabbitMQ's fanout. Right, so RabbitMQ is a very popular queuing system. What I like, also in the previous talk, they touched on the pub-sub architecture. RabbitMQ does that, and in fact, we do exactly that. So what we do is fanout is a certain type of an exchange, and fanout really means that there is one node that can keep it broadcasts an instruction, and any client can subscribe to this exchange and receive it. There's a persistent connection between these two. So it's a broadcaster and a receiver. So what we've got is Django and the twisted services. All you need to do in your code, they have to agree on what the exchange name is going to be. That's all knowledge that it requires. And then because each one of your nodes is controlled by a provisioning system, those nodes, as it should, will set the address, because the nodes have to know which RabbitMQ, where it's actually living and where it needs to communicate to. Okay, so what you've got at the end of this is you've got all these independent nodes, all of them subscribe to the same exchange, ready to receive broadcasts from somewhere. So how we do it, we tell UltraCache, we define a purger, and what the purger does is effectively, okay, first off, a lot of cargo calling code in here, don't worry too much about how these things work. Pico is a way for Python to chat to RabbitMQ, it's just a library. But the important thing that we do is we declare an exchange, which is conveniently called purgatory, and it's called a self-type fanout. And what we And that's pretty much what it does. It gets a path in there, and look what it does. It publishes to that channel, and then we're done. So this will fire when, once again, when the post-save signal handler fires, and it signals that memcache and all those things have to evict keys. It'll also eventually call this with that same path, and it'll tell it, please go and clean up these things. It's time to purge yourself. And this is it's called immediate. Typically, you would rather throw this into a queuing system because this is synchronous, and if something goes wrong there, then your entire request is held up. But for our purposes, this is the simplest example. And then there's a bit of Twisted, which I'm really going to go over quickly, not line by line, because Twisted is hard. Twisted has a lot of, it feels very weird when you read it. But all you really have to take away from this is this service starts up and it connects to an exchange and it listens to it. It connects to that fan-out exchange. So all this looks very hard, and no one in the right mind can actually remember this. I wouldn't be able to write this from scratch. Some more boilerplate really on how to, how you start and stop the service. I'm going to skip right over it. The only thing that we care about is this. We get instructions in from Rabbit, and we get the instruction. In the end, we care about, we get the path, we send an instruction. Remember, this Twisted service runs on the exact same host as the Nginx Web cache. We talk to localhost for that. We tell it it's for this site. It sends a purge instruction to Nginx, and Nginx right at that point cleans itself up. And this happens on all the nodes in your system pretty much simultaneously. Then they're completely clean. So what it means is, once you've implemented this, the moment that someone clicks something, let's say in Django's admin interface, they decide to change an article, you can be pretty sure that all your connected clients, depending on how aggressive your caching headers are, you can quite easily make it so that the browser itself will revalidate every 30 seconds. That's not a big deal because it only does a header request. You can be pretty sure that all your clients will, within 30 seconds to a minute, have access to the latest version that you just decided to change in your CMS. Right. So in a nutshell, that's what it does. Now, we are responsible for Telkom's website, and it's a nice thing to be able to work on, because what we want to do is we're kind of stuck in we don't use our normal infrastructure. We love Ubuntu and Postgres. That's our thing. We are using those guys for that, and we did a fair amount of work to get it to work. Using all these techniques, you can count on, we get about 80% reverse cache hit ratio. It is better because we make use of a technique where if the cache has to be updated, you just serve what you've got for now. So it's actually better to look at the miss ratio. So we end up with a 5 to 10% miss ratio on Telkom. Naturally, not all pages can be cached, as you probably shouldn't cache forms that have serious RF tokens in there. But so we end up with a very low miss ratio, and that's really what we aim for. We want, remember, this means that only 5 to 10% of requests that come in will actually end up hitting Django itself, which is great. We've just saved a shitload of money on servers. There's a downside. Memcache does a lot more traffic. You can count on Telkom. That's sustained all the time. Our chats to the Memcache backend. You're not going to get around it, but luckily you're on an internal network, which is hopefully a gigabit network, and 3 megabytes per second is actually nothing for the real gains that you get. Memcache itself, when things are working nicely, we've found that you can get a 10 to 1 read-write ratio on it. And then what's quite nice is this is not that we would ever do it, but we can technically serve the site on very weak hardware. So how weak? It works on this. We ran a test to serve production data, as in the live site, we replayed real data against the Pi 3. The Pi 3 was fine. The only thing that you can't do is you cannot serve the statics because you kind of exceed the network interface. You can never serve it fast enough over this little 100 megabits per second interface, which is actually closer to 60, I guess. I think it shares the USB bus and Ethernet. It runs over the same bridge. So there's that. But it's pretty cool to be able to do this on a Raspberry Pi. That's kind of where we try and end up with everything. See how far we can push our code. Also, incidentally, the Raspberry Pi brings me to this bit. If you do get an interview with us, as our CIO sits over here, Morgan, we are kind of expanding our team, and if you get an interview with us, regardless if whether we hire you or not, we will give you a Pi. And that was it. This is what I do.
I guess we can, like, as long as people that want to go to lunch can go, and people that want to ask questions can ask questions.
Yeah, go for it.
In case people are hungry.
I'm sure they're hungry. This is like really unfair getting you to compete with food.
Well, you want to survive.
Yeah. Okay, question.
Quick technical question. Does UltraCache...
Sorry.
Sorry, just a quick technical question. Does UltraCache have any built-in mechanism to avoid caching pages that contain CSRF tokens? Use the CSRF token tag.
No, that's left up to the user. I think.
Manually tag them if there's a CSRF form.
What we typically do with those cases is you have to think about, do you really need CSRF? So sometimes you can actually get away with it. It's a let's say your site is purely to capture leads. Then probably you can get away with it. It's not a real security risk if someone were to spoof a lead coming into your site, because you have to follow, the human has to phone them back in any case. However, if you do have a CSRF token in there, then I suggest you take your underlying page and you pull in your form with Ajax in a separate request. Very small payload, you've got your CSRF in there, and then you take it from there.
I'm curious, you're using local caching strategies for, with Django templates, and you mentioned you're using React on the front end, which probably means you're going to use a REST API. How do you use UltraCache with the REST API?
What it can do is, because ultimately when you send things back, now first off, you're not going to have a template to spew out an API for you. So at the moment we don't. We will, I think you would rather fall back to the more classic caching pattern where you do it manually for those. I haven't looked at it. What I do know is I probably won't use a reverse caching proxy for APIs because Nick, who sits over here, has been warning me against it. So, but no, we don't currently. I would love to explore it though, and that is the next step for it.
Yeah, because we used something called Django Johnny Cash.
Yes, I know that is. It's
Cool
a great
name,
name.
cool name.
Yeah, they took all the cool names, man. I wanted to call it Squirrel Shark, but no one wanted to go for it.
Yeah, but since starting using the REST API, it was obviously impossible. Well, except for the database caching, you can do. It was difficult. Yeah.
No, I'd like to give it a bash because actually under I think it can be done. I've done a lot of work with REST framework recently, and I know how to use this work, so it's a nice challenge, and we will be looking at it very shortly.
So you mentioned the engine, or at least what's the fan out?
Yes.
Does it actually plug into Nginx, or is that just for
No.
Twisted and so it doesn't address
It's purely for Twisted. Twisted is the bridge between fan out and Nginx. Yeah.
Cool. And if anyone has any other questions, they can find Haley afterwards.
Yeah.
Lunch is downstairs, and we'll be starting again at 1:45, which is in just under an hour. everyone. There's that open space on machine learning in the Lisbech room this afternoon also, and T-shirts are going to be handed out after the lightning talks this afternoon, so at the end of the day. Cool, thank you.